Today I'm going to solve the previous year GATE questions of heat transfer, and the chapter is conduction. So let's begin. The first question is, consider one-dimensional steady state heat conduction across a wall as shown. The thickness is 30 mm, 0.03 meters. Thermal conductivity is given as 15 watt per meter Kelvin. At x is equal to 0, a constant heat flux whose value is given as 10 raised to the power 5 watt per meter square is applied, and on the other side of the wall heat is removed from the wall by convection. A fluid's temperature is given as 25 degrees Celsius, and heat transfer coefficient H is equals to 250 watt per meter square Kelvin. Temperature in degrees Celsius at x is equal to 0. Okay, be careful that you have to fill the answer in degrees Celsius, not Kelvin. So let's begin. We know that heat transfer rate through conduction is equal to Ka delta T by L. We have the minus sign here, but I'll adjust it with delta T automatically. And the heat transfer rate by convection is equal to HA delta T. Okay, so this flux which is going through the wall will be equal to the flux that will be going to the surroundings. Okay, so first we'll be solving this and this. Q is equals to HA delta T is T2 minus T infinity. Okay, Q by A is equals to H T2 minus T infinity. Q by A is flux, which has been given as 10 raised to the power 5 watt per meter square. Be careful of the units. Sometimes it is given as kilowatt per meter square, so convert it into watt per meter square. Okay, H is given as 250. This is 250. T2 we have to find out. T infinity is given as 25. Putting all the values, we will get T2 is equal to 425 degrees Celsius. Okay, now comparing this with this, that is heat transfer rate through conduction. So Q is equals to Ka T1 minus T2 by L. I have adjusted the negative sign. Okay, so Q by A is equals to Q double dash is equals to K. K is 15. T1 we have to find out. T2 we have just found out upon L. L is given as 30 mm. We have to put it in meters, 0.03 meters. Be careful of the units, be careful. So that implies T1 is equal to, the answer is 625 degrees Celsius. We have to fill the answer in degrees Celsius. We have got the answer in degrees Celsius. Be careful of the units. I am repeating, because if you lose if you lose marks due to silly mistakes, it actually feels pathetic. Let's move on to the next question. It says that a material P of thickness 1 mm is sandwiched between two steel slabs as shown in the figure. Heat flux is given as 10 kilowatt per meter square. So here we have to convert this in watt per meter square, which is 10 into 10 to the power 3 watt per meter square. We'll write it here only. Is supplied to one of the steel slabs. The boundary temperatures are indicated as 500 Kelvin and 360 Kelvin. Thermal conductivity of the steel is given as 10 watt per meter Kelvin. Considering one-dimensional steady-state heat conduction for the configuration, the thermal conductivity of P we have to find out. This is a pretty simple question. Applying the basics, we know that Q is equal to delta T by R total. Delta T is the temperature difference between this end and this end, and R total is the total resistance that will be offered by this steel slab plus this P material and then again this steel slab. Okay, so let this be 1, this be 2, this be 3. Our total will be equal to R1 plus R2 plus R3, where R1 will be L1 by K1A, R2 will be L2 by K2A, and R3 will be L3 by K3A. Okay, so putting these values in this equation, Q is equal to delta T upon L1 by K1A plus L2 by K2A plus L3 by K3A. This A and this A is common, and I'm moving it to this side. Why? Because I need flux. So it will become as Q by A, which will be flux, and I am putting the value of the flux that has been given as 10 into 10 to the power 3 watt per meter square. Delta T has been given as 500 minus 360, okay, upon L1. L1 is 0.02 upon K1. K1 is 10 plus 0.001 upon this we have to find out, plus again 0.02 upon K3. K3 is again 10. Solving this, you will get K2 is equal to 0.1 watt per meter Kelvin. Okay, always in the end when you solve the question, check that in which units you have to fill the answer. Like here we have to fill the answer in watt per meter Kelvin, and we have got the answer in watt per meter Kelvin. Try to solve the question SI units, because whenever you solve the question in SI units, the chances of you committing the error will be less. So try to solve the question in SI units always. Okay, let's move on to the next question. Consider a long cylindrical tube of inner and outer radii Ri, this is Ri, and R0 respectively. Length is L. Thermal conductivity is K. Its inner and outer surfaces are maintained at Ti and T0 respectively. Assuming one-dimensional steady-state heat conduction in the radial direction, the thermal resistance in the wall of the tube is. Okay, this is a direct formula-based question. You have studied that the resistance of the cylindrical wall is Ln R2 by R1 upon 2 pi KL. Okay, here R2 is R0 and R1 is Ri, so that implies resistance offered by this cylindrical tube is equal to Ln R0 by Ri upon 2 pi KL, and which is option, yeah, C. So C will be the answer. So you see that the direct formula based questions have also been asked in GATE. So your formulas should be on your tips. Next question is, heat transfer through a composite wall is shown in figure. Both the sections of the wall have equal thickness L. The conductivity of one section is K and that of the other is 2K. The left face of the wall is at 600 Kelvin and the right face is at 300 Kelvin. Okay, the interface temperature we have to find. This temperature we have to find of the composite wall. Okay, again a pretty simple question. We know that the heat flow rate through this wall will be equal to the heat flow rate through this wall. Okay, again applying the Fourier's law of conduction, I am adjusting the minus sign automatically with delta T. Okay, Ka, let this be 1, let this be 2, so K1A is same because it is a composite wall. 600 minus Ti upon L is same, so L1 is equal to L2 is equal to L. I'm directly writing it as L, which is equal to K2 A Ti minus 300 upon L. Okay, this gets cancelled out, this gets cancelled out. K1 is K 600 minus Ti, K2 is 2K Ti minus 300, this gets cancelled out. Solving this, we get Ti is equal to, the answer is 400 Kelvin. Again, see, this is in Kelvin, we have to find the answer in Kelvin, correct? Okay, so the answer is 400 Kelvin. Pretty simple question on the basics. Let's move on to the next question. Okay, as the temperature increases, the thermal conductivity of a gas, what do you think, guys? Will it increase, will it decrease, or will it remain constant? Okay, before looking at the solution, try this yourself. So now if you have tried it yourself, let me tell you the solution. As the temperature increases, K will increase. Why? Because if you increase the temperature, what happens? The molecules of the gas will start vibrating rigorously. These will start vibrating rigorously. Okay, so as they start vibrating rigorously, they will transport more energy, which implies that as temperature increases, thermal conductivity of gas will increase. The next problem is a plain wall has a thermal conductivity of 1.15 watt per meter Kelvin. Let me draw wall first. Okay, this is my wall. K is 1.15 watt per meter Kelvin. Always take care of the units. Inner surface is at 1100 degrees Celsius, outer surface is at 350 degrees Celsius, 1100 degrees Celsius, 350 degrees Celsius. Design thickness in meters. Okay, let it be L of the wall to maintain a steady heat flux. Steady heat flux has been given, that is 2500 watt per meter square. Very simple question, again applying the Fourier's law of conduction, which is Q is equal to Ka delta T by L with a negative sign. I'll adjust the sign when I'll open this delta T. Q by A is equal to Q double dash, which is K 1100 minus 350, sign has been adjusted, negative sign, by L. Q double dash is 2500, K is 1.15, 1100 minus 350 by L. Upon solving this, we get L is equal to 0.345 meters. So the answer is 0.345 meters. Okay, the next question is, a hollow cylinder has length L, inner radius R1 and outer radius R2, and the thermal conductivity is K. The thermal resistance of the cylinder, okay, so the question has been repeated again. We know that our cylinder is ln R2 by R1 upon 2 pi KL. Okay, so A is the answer, and the formula based question has also been repeated, so I urge you that your formulas should be on the tips. Okay, learn the formulas by heart. Next question. Okay, this is a very good question, an important question, and it's a very amazing question. Two cylindrical shafts A and B at the same initial temperature are simultaneously placed in a furnace. Surfaces of the shafts remain at the furnace gas temperature at all the times. Okay, let this be a shaft. It says that the surface temperature is equal to the furnace gas temperature at all the times. The temperature variation in the axial direction, this direction of the shafts can be assumed to be negligible. The data related to shafts A and B is given in the following table. Diameter is given, thermal conductivity of A and B is given, volumetric heat capacity is also given. The temperature at the center line of the shaft A, this is center line of the shaft A, reaches 400 degrees Celsius after 2 hours. So it reaches 400 degrees Celsius after 2 hours. The time required for the center line of the shaft B to attain the same temperature. Okay, would you like to try it yourself? Very amazing question this is. Okay, uh, if you have tried it yourself, let's solve this question. So you know that this is a transient heat conduction problem. Okay, so whenever you think of transient heat conduction, what comes to your mind? Lumped system analysis. How do you check the whether the lumped system analysis is applicable in this problem or not? You check it by Biot number, which is which states that if Biot number is less than 0.1, you can apply the lumped system analysis. We know that Biot number is equal to HLC by K. Okay, can you find out Biot number? No, you cannot find out Biot number because H has not been given. LC is characteristic length. Characteristic sorry, characteristic length of cylinder is R by 2. Yes, we know this LC, we know this K, but we don't know H. So we cannot say that the Biot number is less than 0.1 or greater than 0.1. Okay, also from the language of the question we can see that the temperature gradients in this direction in this direction in this direction do exist, because the temperature at the center line of the shaft A reaches 400 degrees Celsius after 2 hours. So it takes some time to reach 400 degrees Celsius. Okay, so we cannot apply lumped system analysis here. Now what to do? Now whenever time comes into the picture and you cannot apply lumped system analysis, you have studied another number, that is Fourier number. What is Fourier number? It is a dimensionless time number. Okay, and it's very important, listen it carefully. It comes into the picture when studying conduction that varies over time, when the lumped system analysis approach isn't appropriate. It comes into picture. Okay, when you cannot apply lumped system analysis and studying conduction is varying over time. Okay, so you know that Fourier number is equal to alpha T by LC square. Alpha is thermal diffusivity, which is equal to K by rho Cp. T is time, and LC is characteristic length, which is R by 2 for cylinder. Okay, can we say that Fourier number for shaft A will be equal to Fourier number of shaft B? Yes, we can, because the surfaces of the shafts remain at the furnace gas temperature at all times after they are introduced into the furnace. They have been exposed to the same environment. So FO1 is equal to FO2. Okay, alpha 1 T1 LC1 square is equal to alpha 2 T2 LC2 square. Okay, volumetric heat capacity, joule per meter cube Kelvin. What is this volumetric heat capacity? This is rho Cp. You can also verify it with the help of units. Okay, rho Cp. Rho is what? Kilogram per meter cube, and Cp is joule per kilogram Kelvin, which comes out to be joule per meter cube Kelvin. Okay, so this becomes rho Cp. Now expanding this, alpha 1 is K1 rho Cp1 T1 into R1 square by 2 square, and K2 by rho Cp2 into T2 into R2 square by 2 square. Okay, here in the equation it is R radius, but here it is given as diameter. Please be careful, please be careful. Do not put this value. This is diameter and this is radius. You will lose marks. So R2 is 0.05 and R1 is 0.2 meters. K1 is 40 watt per meter Kelvin. K2 is 20 watt per meter Kelvin. Rho Cp is 2 into 10 to the power 6 joule per meter cube Kelvin. Rho Cp2 is 2 into 10 to the power 7 joule per meter cube Kelvin, and you can put the time in hours. It will not have any effect because here the time will be in hours. You will get the time directly in hours. After putting all the values and solving it, you will get T2 is equal to 2.5 hours. Very amazing question, very good question. So whenever you cannot apply lumped analysis, always, and the conduction is obviously varying over time, always think about Fourier number. Okay, yeah, so let's move on to the next question. The next question is steady one-dimensional heat conduction. Steady one-dimensional heat conduction takes place across the faces 1 and 3. The composite slab is composite. Slabs are A and B. Ka, Kb denote the respective thermal conductivities. Using this data as given in the figure, the interface temperature T2 in degrees Celsius is, okay. So what we can do is we see that the heat conduction rate through this wall will be equal to the heat conduction rate through this wall. We have done this question earlier. I guess it's fifth or sixth question. Yeah. So you see the questions on the same concepts gets repeated in GATE, and it is a pretty simple concept. Like you have to apply Fourier's conduction law in this slab and in this slab. So Q is equal to K A delta T. I will be adjusting the negative sign. Oh, it will get, oh yeah, the sign will get cancelled out. No need to adjust it. K A delta T by L2 L1 K1 A1 delta T1 2 2 2. Okay. So yeah, let A be 1 and B where B is 2. So K1 is 20, area is same, delta T 130 minus T2 upon L1 is 0.1 meter. K2 is 100. A1 and A2 gets cancelled out. T2 minus 30 upon L2 is 0.3 meters. So by solving this, we get T2 is equal to 67.5 degrees Celsius. Pretty simple question. We have done this question earlier also. 67.5 degrees Celsius. So you see that if your basics are clear, you can attempt most of the questions of GATE. But the point is your basics should be crystal clear. Next question. Heat is generated uniformly in a long cylindrical rod. Diameter is 10 mm. Long cylindrical rod. Diameter is 10 mm. D is 10 mm. Or I'll write it in 0.01 meters. At the rate of 4 into 10 raised to the power 7 watt per meter cube. Q generation is 4 into 10 raised to the power 7 watt per meter cube. Thermal conductivity of the rod is 25 watt per meter Kelvin. Okay, under steady state conductions, the temperature difference between the center and the surface of the rod is, okay, again a good question. You can try it yourself. I'll tell you how to do it. It can be done directly by a formula, and the second method is to do it with the basic equation, basic conduction equation. Okay, although the formula has been arrived by the help of that basic equation only, and I do urge you to, I mean, remember the formula in exam, as it will save the time. So I will do it by both the methods. Let's do it by first method, that is directly formula based. Okay, so let this be TW, that is wall temperature, and the center line temperature be T naught. Okay, according to formula, T naught minus T wall is equal to Q generation R square by 4K. This is the direct formula. You should remember it. It will save time. Okay, put the values here. Q generation is 4 into 10 raised to the power 7 watt per meter square. R, this is R, this is T. Be careful, you have to put it in the radius. Okay, so R is 0.005 meter upon 4 into K is 25 watt per meter Kelvin. It comes out to be 10 degrees Celsius. Okay, so this was by the first method, that is directly formula based. Let's do it by the second method. Let me rub it first. I need some space. Okay, 10 mm, 0.005 meters. Okay, so we know that the basic conduction equation, one dimensional, steady state one dimensional conduction equation through the cylinder is 1 by R del by del R delta T by del R plus Qg by K is equal to 0 when I am taking steady state conditions. Okay, although it is 1 by R del by del R delta T by del R plus Qg by K 1 by alpha delta T by delta T. This is temperature, this is time, this is 0 because it has been given that it is a steady state condition. So this equation becomes this equation which has been written here. Okay, so that implies 1 by R del by del R delta T by del T by del R is equal to minus Qg by K. We'll solve this minus Qg by K because Qg has also been given and K has also been given and they are constant. It will be minus 16000000. Okay, taking this R here, that implies del upon del R del T upon del R is equal to 45 R. Yeah, okay, so integrating it, we get R del T by del R is equal to R square by 2 plus C1. Okay, that implies taking this R here, del T by del R is equal to R by 2 plus C1 by R. This becomes, okay, so this is del T by del R. Okay, I have to rub it, although I'll keep del T by del R. Okay, again integrating this equation, this one equation, it becomes T is equal to R square by 2 plus C1 ln R plus C2. Okay, so from, okay, let this be equation 2. From this equation, what we get, that we know that at R is equal to 0, R is equal to 0, delta T by del R will be 0. Why? Because the heat which has been generated inside the cylinder will be flowing like this, from the center line to the outer part, and from this center line to the outer part. So the maximum temperature will be at the center line. We know this. Okay, so at R is equal to 0, delta T by del R will be 0, because here the temperature will be maximum. Okay, so what happens, this becomes 0, delta T by del R is 0, which is equal to, okay, is equal to C1 by R. For this equality, for this equation to be true, C1 has to be 0. Okay, so we get C1 is equal to 0, and the equation for T becomes R square by 2 plus C2. Now solving this equation by applying the boundary conditions. At R is equal to 0.005 meter, T is equal to T wall, and at R is equal to 0, T is equal to T naught. Okay, so first I'll be applying this boundary condition. At R is equal to 0, T is equal to T naught. Okay, so C2, that implies C2 becomes T naught. Okay, now I'll be applying this boundary condition. That implies T is equals to minus, okay, let's cut this down to, so we can directly write this 4 lakh minus 4 lakh R square plus TC. Okay, so T minus TC, T wall minus TC is equal to minus 4 lakh R square. R is 0.005 square, which comes out to be minus 10, and we have been asked the temperature difference between the center and the surface of the rod. We have got here the temperature difference between the surface of the rod and center, so that implies TC minus T wall is 10 degrees Celsius. It's a pretty lengthy method, but if you know the basics, you can actually solve this question. So that is why I'm suggesting that your basics should be crystal clear. You have applied the basic heat conduction equation through the cylinder, and you have got this answer. Although I urge you to remember the formula, because it will save time. Okay, the next question. A plain slab of thickness L, thermal conductivity K, is heated with a fluid on one side, and on one side P and the other side Q is maintained at a constant temperature. TQ is given as 25 degrees Celsius, fluid is at 45 degrees Celsius, Surface heat transfer coefficient is 10 watt per meter square Kelvin. The steady state temperature Tp, we have to find this temperature. Okay, again the same concept that has already been done in the previous question, that the heat flow rate through convection will be equal to the heat flow rate through conduction. Okay, so let's write the heat flow rate through convection, that is HA delta T, and the heat flow rate through conduction minus KA delta T by L. Let it be 1, let it be 2. I'll adjust the negative sign here automatically. H is 10 watt per meter square Kelvin. Be careful of the units. Area is same. I'll cut it down. Delta T 45 minus Tp is equal to K. K is 2.5 watt per meter Kelvin. Delta T2 is equal to Tp minus 25 upon L. L is 20 centimeters, that is 0.2 meter. Solving this, we get Tp is equal to 33.89 degrees Celsius. So with this, I have solved the previous year questions of the chapter Conduction from Heat Transfer. The previous year questions from the year 2014 to 2018.